Jai Jayendra, Namaste and welcome to my channel. Today we are going to solve the 47th question of the problem solving series, which is based on stack, and this is the 7th question of the stack. The difficulty level for this question is hard, and this question has been asked in Google, Amazon, Facebook, Microsoft, and this is a very important question. Recently, in my last interview with Google, this question was asked in the fourth round. I was able to optimize it, but it took a little bit of help from the interviewer. So let's discuss this. So, largest rectangle in histogram. So, look at this example, and this is the bar. Okay. So we have uh, this bar of length 2, the first element. All the bar has equal width, that is 1. Okay, so this is of 2 length, this is of 1 length, this is of 5 length. We need to find the largest rectangle that can be formed using this histogram. Okay, now largest rectangle will include the histograms, all the histograms. Suppose if I take this rectangle, so I can take 5 and then I can take this 5 and 5. Okay, this is the rectangle that is formed. Okay, it won't go this side because we don't have any bar here, right? So this would be the length. So for example, in this one 2, okay, if I take this 2 length, I don't have anything over here, so I can't take this element, the second element whose bar length is height is 1, so I can't take this. So how do I find this? How do I find the largest rectangle? There are many rectangles. You can see one rectangle is this one, okay, and this can go up to here actually, right? So if I need to find the area of this rectangle, so what would be the area of this rectangle? So it starts from 2 and ends with 6. So 4. So this length is 4 and the height we have taken is 2. So 4 into 2, 8. So is this area the maximum that can be formed? So one answer we got 8. Okay. The second answer is 2. Okay. 2. If I take this one 1. So this 1, I can take this 1 can extend up to here and it can extend up to here as well. So this whole thing will be a rectangle. The breadth would be 6 minus 0, 6, and the height would be 1. So 6 into 1, 6. It's 6. It's not more than 8. If I take this rectangle, here this rectangle's height is 5 and the width is 2. So 5 into 2, 10. So this is the rectangle whose area is the most. So we need to return this 10. So 10 is our answer, right? Now how do we find this? What is the approach? What is the intuition? How can we solve this problem? So you can see when I tried for 2, I could not extend because the next element after 2 was lesser than 2, right? So it could not extend, and we don't have any element before 2, right? This is the first element. So the area was 2, right? When I tried for this one, I could extend it up to here till the last, and I could extend this one to the left. Okay, so the whole thing was the part of the rectangle. So what was the area that we could form for 1? It was 6 into 1, 6, right? Height is 1, length is 6. So for this 5, we could not extend here because there is no rectangle. The next rectangle, not no rectangle, the next previous rectangle is smaller than 5. So we cannot extend this. But the next rectangle is greater than 5, right? So we can extend this. So the area became 5 into 2, 10, right? For 6, we could not extend left, we could not extend right, so the area became 6. For 2, we could extend up to this length, up to 2, and here up to 6. So 6 minus 2, 4, and the height is 2, 8. And for this 3, we could not extend towards the left side because this is smaller, and we can't go because we don't have any other element. So for this one, it is 3. So out of this, we saw that this is the max. So we can easily return this, right? So in this way we can find it. So what can we do? For 2, we will go and check what is the rightmost, how much we can extend up to 2, right? Rightmost we will find the leftmost, how much we can extend. That means the next element which is smaller. So for 1 we can see, for 2 we don't have anything. So this next one was actually smaller than this, right? So we could not extend. So its limit was up to 1 only. But for 1 we could extend up to here because there was no element that was less than 1. So we could extend, right? For 5 example, we could extend, we tried to check for 5 what is the next smaller than this. So 6 is not smaller than this, we increased our length, breadth from 1 to 2. But the next one was smaller than this, we could not extend. It is similar to the 42nd or 3rd question that I solved, next greater element. Here we are finding for every element next smaller element. That's index, that is important. So next smaller index and previous smaller index. So once we find the previous smaller and the next smaller index for each of the element, then what can we do? We can, once we have next smaller and previous smaller, then our area would be next minus previous into the height. Say height is this thing, so height of I, whatever we want to check. So next minus previous we will do, and we'll multiply it with its height. For example, 1. So for 1, the next smaller was not there only. So since it was not there, we will give the maximum value, that is 6, right? And for previous, it was this one, 0th. Okay. So we will return this one. Okay. So 6 minus 0 is 6, and height was 1. So the area became 6, right? So that way, for each of the bar, we will find the next smaller and the previous smaller, and then next minus previous into height would be the area formed by that rectangle, and whichever rectangle forms the highest, we will return it. So how we will do this? I've just told it. So we'll go here. So we will have a loop for I equal to 1 to n. We'll have a loop. And for j equal to, so I equal to, if we start from 0 to n, so 1 to n, j equal to I to n. Okay. So for each of them, we will find the next smaller and the higher, previous smaller and the next smaller. Okay. So if I have this, I equal to 0 to n. Okay. J equal to 0 to n, for I equal to 0 to n. Okay. So for if we are here, so we will go towards this side and find its previous smaller. For this one, we don't have the previous smaller, so it would be 0, and we will find the next smaller for this one, and then we will find the area. Okay. So for all of them we will do, and whichever is the area is more, so we will return area is equal to max area and whatever the value that we got, right? The value. Okay. And then we will return it. So what would be the time complexity? So brute force, I hope the intuition and the logic is clear. The time complexity would be order of n square, because for each of them we will go and we will traverse and find the next smaller and the previous smaller, and then calculate the area, and then for this one, for each of them we will go and do it. But this is order of n square, so we need to optimize this. This solution won't work in the interview. So how we will optimize it? What is the logic that we can use? So we have solved the question next greater element. So in the next greater element we use stack. So with the help of stack, we will be able to get the next smaller element and the next previous smaller element in one traversal. Now let's look how can you optimize this in order of n time complexity using stack. Okay, so we'll discuss the same example. So as I discussed, we are finding the previous smaller element and the next smaller element to get the boundary, and then we are using this formula to get the area, and we return the max area. So that we will be finding, so we will find the previous smaller element for each of the elements in the beginning only. Why are we finding the previous smaller element? Just to know, okay, if suppose for example 6, right? So for 6 the previous smaller is this 5, okay, so it can't extend here, right? Because this doesn't have that length. So for example 2, right? 2 can extend here, okay, because 6 has this 2, 5 has this 2, but 1 doesn't have the length 2, right? So the previous smaller for 2 is 1, but what we will do, but this is the boundary, right? So to find the previous smaller for 2, we will just increment it to 2, so that this is the index till which it can stay, right? So for this one, if you see, it doesn't have the previous previous smaller, right? It doesn't have the previous smaller, because the next smaller is so if we find the next smaller for 5, so the previous smaller for 5 is second index, for 2 is second index, but the next smaller for 2 we don't have the next smaller, the number is greater, right? So it will stay up to here only, right? Because this is the area. So that is we will be finding the previous smaller element to get the left boundary of the bar which we want, right? That is the logic. Okay, similarly we will do the same, we will create a next smaller element for each of the bar, and then we will use this formula to get the area in single traversal. So order of n, and then finding this is order of n. So to find this previous smaller element array, we will be using stack, and how we will do is, we will see. Okay, so for example this 2, okay, our stack is empty, we don't have anything, okay, so let's rub this for now. We want to find the previous smaller only. So we don't have anything, so we will be using the stack, and we will be storing the index of the bar, okay, the previous smaller element index of the bar. So for this one we don't have anything, so what we will do, since this boundary is this one only and we don't have any other element, so we will store 0. The previous smaller for 2 we don't have, and since the stack is empty, we don't have anything, we are storing it, so we will insert this into the stack. Okay, so we store the index, okay, here 2, the value is 2. Now we go to 1, okay, so this 1, we check the stack and we have a element here, the 0th index, whose value is actually greater than 1, right? 2 is greater than 1. So since it is greater, so what we don't have the smaller element for this, right? We want the smaller element. So since we don't have the smaller element, so what will happen here? The boundary for this would be, we don't have the smaller element, right? So it can extend up to here, up to the 0, right? Since we don't have this, so our previous smaller would be again 0. How did we find it? We see that this is bigger, so we pop this out. Okay, since 2 is greater than 1, so we'll pop out. Okay, so our stack is empty. So since stack is empty, we don't have anything, we store 0 and we insert 1. Okay, so we have this one index whose value is 1. Okay, it might be confusing in the beginning, you'll understand it. Okay, when we go to this 5, 6, 2, 3, everything will be clear. So now the next element is 5, okay, the second index. Now for this 5, we want to find the previous smaller element. So we have this stack that stores the element, and we pop the value for this is 1. So 1 is actually less than 5, which we want, okay. So this is the previous smaller element for this. So what we do, we store its index plus 1 value. Why? Because since we have this is the smaller element, so the boundary for this will be actually up to this, right? We can't go here, right? 5 can be stored up to here only. So this is the boundary, the left boundary for 5 is this one. So the value would be actually 1 plus 1, 2. You understand? So when we find this value, whatever the value is there, stack dot top here, 1, okay, and we will increment 1, okay, because we want to get the boundary. We are interested in this part, okay. So we will store 2, and what we will do, since we have this 1, we have got this boundary, so once we get it, then we need to pop this out, okay? Because this stack will always be in a increasing order. Because if the next one is greater than this, then there is no point of checking that. Now we want interested in finding the smaller element, right? So so for this one, so if the next number is actually 5 is greater than the next number, so anyway it can't, the next number won't be smaller than this, right? So we will pop this out and then we will store the fifth index, that is second. And what would be the value for the second? The value would be 5, okay? So now for the third element, okay? 0, 1, 2, 3, 4, 5, okay? So for the third index, okay, its value is 6 and we see what is the value here, 5. So 5 is actually less than 6, which is the previous smaller to this. So we've got the answer. And what is its index? 2. So 2 plus 1, okay. So 2 plus 1, that is 3. So this is the left boundary for 6, okay. So for 5, the left boundary was this, okay. Now 2, okay. So we have got this. So we will store this. Okay. So so this is actually this 2. We should not pop out this value, 1 value, okay, because 1 is actually less, right? It has to be increasing, so it was actually less only. So it would be in this order, because we will understand why I am not popping out this one. So since this is smaller, so this should be there in the stack, and we will insert the next one, which is 6. Okay. Now 2. Okay. Fourth index. 2 we check with in the stack. 6 is here. Everything will be clear. So 6 is actually greater than 2. It is not smaller than 2. Right? So what will happen? Since 6 is greater than 2, we are interested in finding the previous smaller. So we can include this boundary. The boundary will extend. Okay. So we'll pop this out. Okay. So we'll pop this out. 6 is greater than 2. Next, what is the element? 5. 5 is also greater than 2. We are interested to find the left boundary, the previous smaller. So we'll pop this out. What is the next boundary? Element 1. Okay. So 1 is actually less than 2. So what is the boundary for 1? What is this? So what would be the left boundary? So its index is 1. So we will increment it plus 1. So it would be 1 plus 1, 2. Okay. So this would be the boundary, right? This up to, it can extend up to this. So it would be 1 plus 1, 2. Okay. And then we will store this. Okay. We will not pop this out, don't do that mistake, and we will store this push. So the index is 4 and the value is 2. Now for 3, for 3 we will see for 3 this element, fourth element, when we the 2 is actually less than 3. It is not great. The 3 is not less than 2. Okay. So since it is one second. So for 3, the next element is the smaller element, right? We want to find the smaller element. So since it is smaller than this, so what would be the index, left boundary for this? Its index, fourth index, right? So fourth index plus 1. Okay. Because we need to find this boundary. It's smaller, it can't go over here. So 4 plus 1, 5. So this would be the previous smaller elements indexes, right, for each of the bar. Similarly, we will find the, using stack, we will find the next smaller element index. Okay. We'll use the same operation. We will begin from right side, and you can just easily say for 3 what would be the next next smaller element boundary. We don't have anything, right? So it would be 5. Same logic we will use. we don't have anything, so it would start from the number of elements that we have, the fifth bar, okay. And for 2 we have it can extend up to here, so we have the next for 2 also we don't have the next smaller element to the right, so it will also extend up to 5. So for 6 we have the next smaller element, so its index is 4, so here we will decrement it, okay. 4 minus 1 3. For 5 we have the next so we will push this, so the next element greater is 6, so we don't have the next smaller, okay. So the next smaller is this 2, okay. This one is greater, so then we pop this out, so we see this is the smaller than 5, okay. So its index is 4, so 4 minus 1 3, okay. And for 1 we can see all of them are actually greater than 5, so it's greater than 1, so its index should be 5, right. Yes, right. And then for this one 2 we what is the next smaller, this is the next smaller, right. So this 1 minus 1 0, right. This is the smaller, so 1 minus 1 0, okay. So in this way we found the previous smaller and the next smaller, and then we will use this formula to find the area, right. So in this way we will be able to find the area, and we can see that the area will be max for this second bar, okay. So 0 1 2 3 4 5, so 3 minus 2, actually we need to do plus 1 here, okay. 3 minus 2 plus 1 into a of I. Why we are doing plus 1? We need to do it because we are finding the area, so its length is also 1, right. The bar's its length itself is 1, okay. So for example, so for 6 the previous smaller is we don't have previous smaller, we don't have next smaller, okay. So both when we don't have both the values, so it becomes same, right, and we need to have this value, right. So it will be right minus left plus 1 into a of I, and in that way we can see that for this bar, okay, fifth bar, the area of fifth bar, area of second bar, right. So for this one we can see that we can find it in order of 1, that is 3 minus 2 plus 1 into 5, which is 10, okay. So in this way we can find the area of the largest rectangle in order of n. So let's directly go do the code walkthrough and understand this, and I'll directly run it. If you want to try it yourself, please try it yourself. The link to the question has been given in the description. Here is the code walkthrough of the 47th question, largest rectangle in histogram in lead code platform. You can see this question is very common in these companies, and the difficulty level is hard. And let's look at you can see these examples. We discussed this example as well, in this example only. And then let's look at the code, okay, and let's understand it line by line. We have the height here, we took the stack, we have this left array and the right array, okay. So we traverse we run a loop, and then we check in this if the stack is empty, and if the stack is not empty, and height of stack dot top, if it is greater than height I, then we pop the elements. What does this mean? So when the stack is not empty, say for example this 6, when we are in the 6th, this bar, okay, whose height is 6, and we see that this okay, so height of stack dot top is greater than height of I, okay. So let's not take this example, let's take say this example when we are in 2, okay. And when we see, and these two 1 5 6 are already there in the stack, and when we see that height of stack dot top, so in the top we have 6, if it is greater than height of I, right? So when we pop this out, why? Because this, we want to find the next smaller element in the beginning, previous smaller element. So since this will include this boundary, so we'll pop this out till the time we find the element which is smaller than 2, right? So that we can increment it and we can have our boundary from here. You get it, right? So this is the operation where we pop the elements, okay? When we don't find the previous or the left smaller element, okay? So when this, if we see that the stack is empty, then we add the left small I value as 0. So in the beginning only we can see the stack was empty. So we initialize the left, if the stack is empty, the left small, for that bar, the left small will be 0 because nothing is there in the stack, okay? Else, let me just beautify this. Else, if it is not empty, then the left small would be stack dot top plus 1, right? So here when we see for 2 6 was greater, 5 was greater, 1 was smaller, okay? So when we get the element which is not smaller than the height, then we increment its index at stack dot top plus 1 because this is the boundary, right? So it becomes 2. So that is what we have done over here, and once we do this, we push the index to the stack, okay? So in this way we find the left small, and for we pop the elements in the stack so that we can reuse this same stack to find the next smaller element, the right side, the right small, okay? So for right small, we run the loop from the right part, and then we see the stack if it is empty, if it is not empty, and the height of stack dot top, same logic, right? If it is greater than equal to, this is same to this. If the height of stack of 2 is, it is greater, we want to find the smaller, so we pop the elements, right? If the stack is empty, then what do? We make the right small value as n minus 1, right? So here n minus 1 is the index, right? The n is the size, so 6 minus 1 5, okay? For this one, right? So we find the right smaller, and then if the stack is empty, we get the right small as n minus 1, and if its stack is not empty, then we decrement it, right? As we discussed, stack dot top minus 1, and we push the elements into the stack, and the max area becomes max a, we traverse the array, and height I into right small minus left small plus 1, as I said, the length of the bar itself, right? And we return the max bar, okay? So let's run this. For this example, we can see we have got 10. For this second to 4, we have the output as 4, okay? So this 4 or this 4 both are of the same area, and we will submit this code then, since it looks good. So this code has been accepted. I hope you have understood the explanation. If you have not, please please watch the video again and practice this question. This is an important question. Okay, then see you all soon in the next video where I'll be explaining the 48th question of the problem solving series and the last question of the stack maybe. Okay, Jai Janendra.